the James Webb Space Telescope has spotted a black hole that shouldn't exist one devouring matter faster than physics allows. How can something so massive break the very rules that define the universe? Tonight we'll uncover what makes GS-3073 one of the strangest discoveries yet. If you enjoy this exploration, please like, subscribe and share, and tell us in the comments, do you think we've truly reached the limits of our understanding? Thank you for watching. Now, let's begin. The scene opens on a universe that is young by later standards, yet already busy with light. Gas between galaxies is not fully transparent. Most of it is hydrogen, the simplest atom which at early times holds onto its electron. When a photon with enough energy arrives, it can strip that electron away and leave an ion behind. This process is called ionization. Ionization is the long phase when the first generations of stars and accreting nuclei flood space with such photons and push the neutral fog toward a clearer state. In this era, the intergalactic medium is patchy. Islands of ionized gas expand around sources and slowly connect, while farther regions still hold a small but important fraction of neutral atoms. Along any line of sight, the transmission of light depends on whether it crosses an ionized bubble, the edge of a bubble, or a more neutral zone. For a distant galaxy, these differences appear as dark absorption troughs, punctuated by narrow windows where light makes it through. Observers call these windows transmission regions, and they map the progress of reionization. The background bath of ionizing light, called the ultraviolet background, sets the baseline conditions everywhere between the bright islands. It is not a uniform field laid down all at once. It builds up gradually as more sources turn on, and it varies with position because matter is clustered. Close to groups of young galaxies, the background grows stronger. In quieter voids, it is weaker. This uneven field controls how far an ionizing photon can travel before it is absorbed. That characteristic distance, the mean free path, lengthens as the neutral fraction drops, so later times show wider transmission windows. The background does more than illuminate, it heats. When a hydrogen atom is ionized, the freed electron carries away energy and then shares it with nearby particles through collisions. The gas warms to tens of thousands of degrees, enough to swell against gravity in the thinnest places. After the flood of photons subsides, the gas cools again through radiation from atoms and ions that recapture electrons or tumble between energy levels. The result is a gentle relation between temperature and density across the cosmic web. Low-density regions stay warm and smooth. Higher-density filaments cool more efficiently and can continue to gather. These thermal conditions matter for every young galaxy. Cold gas falls along filaments into growing halos of dark matter, but the ultraviolet background sets a floor under the temperature of the inflow and changes how quickly it can settle. In the smallest halos, heating from the background can even hold gas out, delaying the onset of star formation. In larger halos, gas still arrives, but with altered pressure and ionization state, which in turn shapes how it sheds energy. Cooling pathways depend on which atoms and molecules are available to radiate away heat. Atomic hydrogen can cool hot gas through the light it emits when electrons jump between levels, but at lower temperatures, molecules like molecular hydrogen can take over. The same early radiation fields that ionize hydrogen also produce a band of light that breaks up molecular hydrogen. Thus, the early ultraviolet background both opens transparency and closes certain cooling channels, guiding where and when gas can collect. Reionization proceeds inside out on many lines of sight. Clusters of galaxies and accreting nuclei carve growing spheres through the neutral medium, and those spheres overlap into networks. Edges remain important. At the outskirts of each sphere, the neutral fraction rises, and photons redshift into energies that interact more strongly with hydrogen. That edge can imprint a broad wing on spectral features from background sources, a sign that the universe there still holds significant neutral gas. Inside the ionized regions, the background allows fainter features to pass. Metal lines from oxygen, nitrogen, and carbon can appear, each tracing specific temperatures and ionization states. These elements were forged in the hearts of stars and then dispersed by winds and supernovae, so their presence signals that the cycle of birth and feedback is already underway. Even so, the background keeps an overall clarity that was not present earlier. The timing of reionization is stretched over hundreds of millions of years. It is not a single switch, but a mosaic, changing tile by tile. Some sectors of the sky clear earlier, some later, depending on where sources gather. Large-scale structure gives this pattern a natural order. Filaments feed nodes where halos are most massive, and those nodes host the brightest sources of ionizing light. From such nodes, waves of transparency move outward. Between the nodes, long tracts of space remain dimmer and more neutral for longer periods. Against this evolving canvas, any individual galaxy sits in a local window, whose clarity depends on its neighbours and its own output. A galaxy embedded in a strong background will show more transmitted light near the wavelength that neutral hydrogen would otherwise absorb, while one in a quieter region will appear more muffled. The ultraviolet background also sets the stage for how gas behaves at the edges of galaxies. It changes the balance between pressure and gravity in the outskirts, making the boundary between a galaxy and the intergalactic medium softer and more extended. Gas that leaves a galaxy through winds travels farther when the surrounding medium is warm and thin, and gas that tries to fall in faces more resistance when it is already warm. In practice, this means that the rate at which fresh material can reach the inner parts is modulated by the background field and its local strength. Measurements of the background come from several lines of evidence that fit together like parts of one scene. Quasar spectra reveal forests of absorption features that track the neutral hydrogen along the path. The spacing and depth of those features change with time and with the growth of ionized regions. Faint galaxies contribute through their collective light, which adds to the field even when individual sources are too dim to study in detail. Radiative transfer models connect these pieces by following how photons move through clumpy gas. Although exact numbers are still refined, the direction is clear. The background grows stronger with time across the reionization era and becomes more uniform as overlapping bubbles merge. By the time the universe ages by a few 100 million years beyond the first lights, most sightlines pass through ionized gas, with only small pockets of neutral material left. This does not erase the imprint of earlier phases. Residual patches of higher opacity can persist near dense filaments, where gas recombines more often. The interplay between ionization and recombination continues, governed by the balance of photon production and the density of the medium. Temperature, density, and ionization set the pace of chemistry as well. Ions of carbon and oxygen form and break in step with the background, and their emissions become signposts of the thermal history. The clarity brought by reionization has another quiet consequence. It allows radiation from compact central engines and hot young stars to travel farther without being swallowed by neutral gas. Even when that radiation is filtered by dust within galaxies, the intergalactic path is less obstructed than before, so observers can trace multiple features across wide ranges of wavelength. All of these conditions define the window through which a high redshift source is seen. The ultraviolet background, the degree of ionization, and the thermal state of gas shape every spectrum, set contrast for every image, and regulate the journey of matter from the web into forming galaxies, Astronomers first meet GS-3073 as a set of faint shapes and colours in deep images, then as a pattern of features in dispersed light that carries the imprint of atoms and motions. The path from a field crowded with distant sources to a single object flagged as an accreting nucleus begins with selection. Imaging from a space telescope provides a grid of filters that sample the spectrum at many narrow windows. A young galaxy at high redshift shifts its ultraviolet light into the near-infrared. This shift moves a sharp drop caused by hydrogen absorption between filters in a way that depends on distance. Observers call this a dropout technique. When a source is bright in redder filters, but falls away in bluer ones, the pattern points to a likely high redshift candidate. Photometric redshift estimation formalizes this step by fitting template spectra to the measured colors and returning a probability distribution for distance. The fit also separates stars' galaxies and possible active nuclei through differences in their broad shape. Stars in the foreground show distinct curves and often appear as point sources with a compact profile. Galaxies appear more extended, though at great distance even a galaxy can look almost point-like. In the first pass, GS-3073 stands out as a compact source with colours consistent with a distant object beyond the time when hydrogen in space absorbs much of the ultraviolet. The next move is spectroscopy. A spectrograph takes the light and spreads it by wavelength to reveal lines which are narrow or broad peaks, and valleys caused by atoms absorbing or emitting at precise energies. The rest frame is the spectrum as it would appear at the source. The observed frame is what arrives after cosmic expansion stretches every wavelength. Moving from imaging to spectra allows a secure measurement of redshift by matching known transitions to their shifted positions. In early galaxies and active nuclei, strong lines from hydrogen, carbon, nitrogen and oxygen appear in the rest ultraviolet. Helium-2 is a transition that needs hard radiation to excite, and its presence signals energetic photons that can come from an accretion engine. Broad permitted lines are features whose widths reflect high velocities close to a central mass. When permitted transitions such as carbon-4 or magnesium-2 spread over thousands of kilometers per second in velocity space, the width points to gas moving quickly under gravity near a compact object. In GS-3073, broad components accompany high ionization lines, and together they mark the source as an active nucleus rather than a quiet stellar system. Before accepting that label, the pipeline checks several alternatives. A starburst with many hot young stars can create strong ultraviolet light, and winds from such stars can broaden some features. Yet stellar winds tend to produce profiles with characteristic shapes that differ from the smooth, very wide bases seen in active nuclei. Shock fronts in emerging galaxy can also excite lines, but they rarely generate the full set of high ionization signatures at the required strengths across the same region. The spatial profile in the spectrograph offers another clue. If the broad component is concentrated at the source center, and the narrow components are more extended, the geometry aligns with a compact engine surrounded by more widespread gas. Line ratios provide a further test. Ratios between nitrogen, carbon and helium lines depend on both the radiation field and the abundance pattern of the gas. Nitrogen can be enhanced when stars have already processed material and returned it to the interstellar medium. A nitrogen loud pattern suggests rapid chemical evolution near the nucleus. In GS-3073, elevated nitrogen relative to carbon and oxygen supports the view that the gas close to the center has been enriched and is exposed to hard radiation. The continuum shape across the near-infrared helps separate dust-reddened starlight from a flatter power law component often linked to an active nucleus. spectral energy distribution fitting a technique that compares the measured continuum to combinations of stellar populations, dust screens, and an active template quantifies these contributions. When the fit demands an additional non-stellar component with a slope typical of accretion light, the case strengthens. Variability. A common signature of accretion is harder to use at these distances because repeated deep observations over long times are rare, but even without time series, the spectral and colour evidence can reach a robust classification. Data quality flags and contamination checks are part of the identification step. Slit or microshutter spectra can include light from neighbours if alignments are imperfect. The pipeline models the point spread function across wavelength to ensure that the broad bases are not artifacts of overlapping sources or instrumental scattering. Sky subtraction and background estimation are tuned to the low surface brightness regime of very distant targets, where small residuals can mimic weak features. Independent reductions test that the lines persist across methods. When available, multiple dispersers or grating settings confirm that the same features recur at the expected positions. Imaging at higher resolution supports the spectral picture by mapping any resolved structure. If the source shows a compact core embedded in a faint host, the morphology matches an active nucleus embedded in a small galaxy. If lensing by a foreground mass were present, one might expect arcs or mirrored images. The absence of such signatures reduces the chance that magnification is confusing the interpretation. Photometric apertures are varied to check that the measured colours are not biased by nearby objects. The set of measurements then converges on a secure redshift and a classification consistent with an accreting black hole. With the identity established, observers extract the physical quantities that guide the rest of the analysis. The width of a broad line combined with a measure of the continuum or a line luminosity provides a mass estimate through empirical relations calibrated at lower redshift. These relations carry uncertainties because they are anchored in reverberation mapping of nearer systems and assume that similar structures exist here. The approach remains useful as a comparative tool. The total luminosity across the spectrum indicates how strongly the source shines. Corrections for dust adjust that value upward when reddening is present. The slope of the ultraviolet continuum can hint at both dust content and the intrinsic shape of the emission. The presence of high ionization lines requires photons of high energy, and the ratios between lines trace the hardness of the source. Together, these measurements outline a coherent view of a compact engine feeding at a luminous rate inside a small chemically active host. Each piece of evidence is drawn from direct observables colours across filters, positions and widths of lines, shapes of profiles, spatial concentration in the two-dimensional spectrum and the balance between stellar and non-stellar components in the continuum. The chain from initial selection to identification is careful at every link. It begins with colour patterns that point to great distance, moves through spectral confirmation of redshift, separates stellar processes from accretion through line widths and ionization, and establishes a compact centre with a surrounding reservoir of gas. In this way, GS-3073 stands in the sample as an early active nucleus found by imaging certified by Spectra, and characterized by a set of features that match the expected signatures of a feeding black hole embedded in a young galaxy. The host of GS-3073 appears as a compact glow with faint extensions that blend into the background of distant light. Imaging in bands that capture the rest, ultraviolet highlights regions where young stars form, while bands that reach farther into the rest optical bring out a smoother body that traces older stars. The point spread function, which is the blur imposed by the optics and detectors, broadens every source by a small amount. Careful modelling removes that blur to reveal the intrinsic shape. After this correction, the host keeps a small apparent size with a bright centre and a profile that falls away gently rather than sharply. The half-light radius, defined as the radius that encloses half of the total light, sits well within the central region, leaving a low surface brightness envelope that is hard to follow against the noise. Even so, stacked views and careful background subtraction show that the light does not end abruptly. It tapers outward in an asymmetrical fashion, hinting at a system that is still settling. The axis ratio, a simple measure of how elongated the image appears, suggests a moderate inclination rather than a round face on view. Position angle measurements, which describe the orientation of that elongation, remain stable across filters, a sign that the same structure underlies both the young and older components. Within the central arc, small clumps ride on top of the smoother light. A clump in this context is a knot of star formation that appears as a bright patch in the rest ultraviolet. These clumps are common in young galaxies that gather gas quickly. They form where local density rises and cooling speeds up, and they can migrate inward as they lose angular momentum. In GS-3073, the clumps are not arranged in a regular pattern like the arms of a spiral. Instead, they sit off-center and show different contrasts in different bands, which implies different ages or dust content. A redder clump might hide young stars behind dust, while a bluer one might be less obscured or slightly younger. The core itself remains compact after deblending the central active light, a two-component model that fits a point-like center plus an extended host reproduces the observed shape. The point-like part dominates in the bluest rest wavelengths and eases in the redder ones, while the extended part grows more prominent as the observing bands move to longer wavelengths. This behavior matches a luminous nucleus embedded in a small galaxy whose older stars contribute more to the redder light. The surface brightness profile of the host can be described with a simple law that ranges between a steep central rise and a shallower outer slope. Many young galaxies at similar distance show low values of the shape index associated with disk-like structures, but the fit here does not force a perfect disk or a perfect spheroid. The residuals of the fit, which are the small differences between the model and the data, show lopsided features on one side and a faint tail on the other. These residuals could reflect minor interactions in flow along a filament or internal instabilities. They situate the host in a class of systems where smooth global structure and patchy star-forming regions coexist. Dust leaves its mark across the image. Where dust is thicker, light at shorter wavelengths is dimmed more strongly, shifting the local color. A smooth gradient across the central kiloparsec hints at a dust lane or a richer central reservoir that screens the inner stars. Yet the total attenuation remains moderate since the core still appears in the ultraviolet, and the overall color does not turn extremely red. The pattern supports a scenario in which the central regions hold both dust and gas, but do not bury the starlight entirely. On scales just outside the bright core, the image shows a subtle twist in the isophotes, which are contours of equal brightness. Such a twist can arise when the inner and outer light distributions are slightly misaligned, perhaps because stars formed in different episodes, or because fresh material settled at an angle to the existing mass. The absence of a clear bar or grand design spiral is not surprising at this stage given the short dynamical times and the influence of frequent inflows. The host may still be assembling a stable disk or spheroid, and the current view catches it mid-stride. The environment around the host does not crowd the frame with bright companions. A few faint smudges lie within a small projected distance, but their colours differ enough to cast doubt on a direct association. Without a clear set of multiple images or arcs, strong lensing seems unlikely, and the measured sizes and shapes can be considered intrinsic to the galaxy rather than stretched by foreground mass. The background is smooth after masking, and the noise properties match expectations for deep exposures, which lends confidence to the low surface brightness features. Photometric apertures of varying size recover consistent total fluxes and growth curves, level off as expected when all the light is included. Structural measurements hold steady across independent reductions, a sign that they are not artifacts of one pipeline. The rest, optical bands which better trace the older stellar mass, present a rounder appearance with fewer pronounced clumps, while the rest, ultraviolet bands, show the patchiness more clearly. This difference is natural since new stars burn bright in the ultraviolet, and older stars contribute most to the redder light. A comparison of the shapes in these two regimes suggests that the mass-carrying component is smoother and slightly more extended than the high-contrast star-forming patches. In simple terms, there is a calm body with a few bright sparks on top. The central light concentration lines up with the centroid of the broad line region, seen in spectra to within the uncertainties of alignment between imaging and spectroscopic slit placement. This alignment supports the view that the active engine sits at the photometric center of the host, rather than in a displaced knot. Small offsets would not be unexpected in a system that is still growing, but the present data do not require them. Color maps built from pairs of filters indicate a gentle inward reddening consistent with a dustier or older central population. The gradient is shallow, not a sharp break. That smoothness argues for a mixture of stars and dust rather than a thin, prominent screen. On the largest scale that the data can probe, faint asymmetries persist. A wedge of light extends a little farther on one side and a dim spur bends away on the other. These shapes can be signs of minor disturbances or the footprints of gas streams that have fed the galaxy. Because light at these faint levels is near the detection limit, any interpretation stays modest, yet the repeated appearance of the same features across reductions keeps them in view. The overall impression is of a young galaxy with a compact heart, a modestly elongated body, scattered star-forming clumps and hints of outer irregularities. Its structure is neither featureless nor orderly, but consistent with rapid growth in an era when fresh material arrives along the cosmic web. Within this structural frame, the central compact source sits naturally embedded in a body that can supply fuel and absorb energy, while the star-forming patches trace the places where gas turns into new light, against a background that reveals the settled mass underneath. Ionized gas spreads across the host of GS-3073 as a diffuse glow and as knots where energy concentrates. Ionization means that atoms have lost one or more electrons. In a galaxy like this at early times, ionization is driven by two main engines. Hot young stars emit ultraviolet light that can kick electrons free from hydrogen and other elements, and a compact nucleus emits even harder radiation that reaches deeper into clouds. When electrons and ions meet again, they emit light at very specific wavelengths. Those narrow features are called emission lines. They mark where gas is present and how it is excited. Observers map these lines across the face of the galaxy to trace structure and motion. The most prominent beacon of ionized hydrogen is the line that astronomers call Lyman alpha, a transition that happens when an electron falls to the ground, state from the first excited level. This line is strong, but it scatters easily from neutral hydrogen, so its appearance depends on how much neutral material lies along the path and on the small-scale shape of the gas. In a young object, patches of outflowing gas can turn the line asymmetric, and small dust grains can dim it. Yet even with these complexities, the pattern of extended Lyman alpha light often outlines regions where ionized gas fills space around stellar clumps and the central source. Other lines come from atoms that have lost multiple electrons. Doubly ionized oxygen, triply ionized carbon, and quintuply ionized oxygen require photons of higher energy to exist. These are called high ionization lines, and they respond quickly to the hardness of the radiation field. By comparing their strengths to hydrogen lines, one can separate zones dominated by hot stars from zones influenced by an accreting nucleus. In GS-3073, the map in these lines shows a compact core where the highest ionization states cluster, wrapped by a more extended envelope where lower ionization states keep a steady light. The structure suggests that the central engine affects gas near the nucleus, while star formation contributes more widely across the host. Integral field spectroscopy delivers both spectra and spatial information at once. Each tiny spatial element carries a small spectrum. When these pieces are assembled, one obtains a data cube that can be sliced by wavelength to make images in single lines, or by position to make kinematic maps. The ionized gas on galactic scales reveals itself in such slices as filaments that thread outward and as arcs that bend around the core. The surface brightness declines with distance from the center, yet faint features persist beyond the radius where the stellar light becomes hard to track. This difference arises because ionized gas can be lit by photons that escape through channels carved by winds, or by low-density paths reaching farther than the starlight that simply adds up in the smooth body. Diagnostics based on line ratios provide temperature and density estimates. Electron temperature influences the balance between collisional excitation and recombination, and certain pairs of lines respond in opposite ways to temperature. Electron density affects how often excited states collide before they can emit light, which changes the relative strengths of lines that come from closely spaced levels. In practice, lines from doubly ionized oxygen, singly ionized sulfur and singly ionized nitrogen offer such tests, and though exact values carry uncertainties at these distances, the pattern of ratios indicates gas that is warm and of moderate density consistent with extended regions under the influence of both stellar photons and a central source. The geometry of ionized gas also encodes motion. When gas moves toward or away from the observer, the emitted light shifts slightly in wavelength through the Doppler effect. Velocity maps built from line centers show gradients across the galaxy. In GS-3073, a gentle shear runs along the major axis of the host, and superposed on that shear are local patches with larger departure from the central value. The shear can mark ordered rotation in the extended gas, while the patches often indicate flows pushed by pressure or pulled by gravity. Line widths offer a second view of motion. The width at each point blends thermal agitation, turbulence, and unresolved flows within the spatial element. Wider lines near the core speak to stronger stirring or to overlapping components along the line of sight. Narrower lines farther out suggest quieter conditions, though occasional broadening along thin features hints at channels where gas is being driven outward. Ionized cones appear in many nearby active galaxies. They form where the central source shines through polar openings in surrounding material. If a similar structure exists here, it would imprint two lobes of high ionization gas on opposite sides of the nucleus. The present maps show a brighter sector to one side and a fainter sector to the other, offset from the host minor axis. This asymmetry can be a sign of one illuminated side and a more shadowed side, or of different gas columns along the two directions. The detailed shape depends on how dust and dense clouds block or filter the radiation, and on the angle between the line of sight and the engine. Extended ionized gas often connects with the neutral and molecular phases that provide fuel, Along the edges of bright regions, filaments fade into zones where emission from singly ionized carbon and other coolants arises in the far infrared. Although those coolants are not directly mapped in the ultraviolet, their presence is implied by the need to carry away energy as gas recombines and cools. The ionized skin of a cloud can shield the interior from the hardest photons, allowing molecules to survive deeper inside. In this way, a single structure can present an ionized face to the central source and a neutral core that later drifts inward or forms stars. The degree to which the nucleus contributes to the extended ionized light can be tested by comparing the spatial fall-off of high ionization lines to that of hydrogen lines. A steep decline from the center in the former relative to the latter generally points to central dominance, while a more even pattern points to distributed hot stars. In the case of GS-3073, the high ionization traces fade faster than hydrogen recombination light, yet they remain detectable beyond the inner kiloparsec. The mix suggests that both engines operate with the nucleus setting the tone near the core and star formation filling a broader stage. Nitrogen lines deserve special attention because earlier measurements show elevated nitrogen relative to carbon and oxygen close to the nucleus. On galactic scales, nitrogen emission still appears, but the ratios relax toward values more typical of young stellar regions. This gradient carries information about chemical processing. Nitrogen grows in abundance when generations of stars have had time to seed the gas, so a rise toward the center indicates that material near the nucleus has been cycled and enriched rapidly. The smoother outer values reflect a younger or less processed reservoir. The ionized gas also carries clues about dust content. Balmer line ratios, which compare different hydrogen transitions, are sensitive to reddening because dust dims shorter wavelengths more. With rest, ultraviolet access similar leverage comes from comparing resonant and non-resonant lines. Where dust is thicker, resonant lines that scatter many times before escaping are suppressed more strongly than non-resonant lines that depart directly. Patterns in GS-3073 match a picture in which dust is present but not overwhelming on galactic scales, with slightly higher attenuation toward the inner regions, and a patchy distribution that aligns with clumps seen in the ultraviolet images. Energy input from stars and from the nucleus heats, gas and drives motion. Ionized shells around young clusters expand until their pressure matches the surroundings. In places where multiple shells overlap, the emission brightens and line widths increase. Near the compact center, radiation pressure and thermal pressure can push channels into the gas, giving photons preferred exits and sculpting the arc seen in the maps. Where an outflow crosses a denser filament, ionized features kink or brighten, and downstream of such interactions, the gas cools and recombines, leaving a tapering trail of emission. The outermost detectable regions carry low surface brightness and low line widths. They track the transition from the galactic environment to the more tenuous medium beyond. Small ripples in velocity there reflect the large-scale potential rather than local driving. Across all these scales, the ionized component acts as a tracer that reveals where energy is deposited and how gas responds under the changing light of early times. Chemical clues gather near the center of GS-3073, where narrow lines rise from gas that sits farther from the core than the fastest, broadest clouds, yet still lies within the reach of hard radiation. This region is called the narrow line region. It is a zone where electron densities are high enough to make emission efficient, but low enough that excited atoms can radiate before collisions knock them into other states. In such conditions, line ratios between different elements and ionization stages turn into a readable code that reports on composition, radiation hardness, and the pace of recent processing by stars. Composition, often called metallicity in astronomy, means the fraction of mass in elements heavier than hydrogen and helium. These elements are forged in stars and return to gas through winds and supernovae. Nitrogen holds a special place in this story because its abundance can grow in a way that depends on how much carbon and oxygen are already present. At low overall metallicity, nitrogen forms in ways that do not strongly depend on prior enrichment, and is often termed primary. At higher metallicity, nitrogen production tracks existing carbon and oxygen, and is termed secondary. The switch from primarily primary to increasingly secondary behavior imprints a steep rise in nitrogen relative to carbon and oxygen as the gas becomes more enriched. This pattern makes nitrogen line ratios sensitive probes of rapid chemical evolution near an active nucleus. In GS-3073, lines from nitrogen appear in both low and high ionization states. A line from triply ionized nitrogen sits among other high ionization features in the rest ultraviolet, while lines from singly ionized or doubly ionized nitrogen trace zones of milder radiation. Ratios such as nitrogen to carbon and nitrogen to oxygen are measured by integrating the flux in each line after subtracting the local continuum and correcting for dust. Dust corrections matter because shorter wavelength lines are dimmed more strongly than longer wavelength lines, which can tilt ratios if not accounted for. Balmer line pairs in the optical rest frame offer one route to estimate reddening, but at these distances observers also use comparisons among close ultraviolet lines when available to limit systematic errors. After these steps, the nitrogen ratios in the narrow components of GS-3073 sit above those found in many star-forming galaxies at similar redshift, and above those in outer parts of the same host. The elevation is strongest within the inner region and declines with distance from the center along the slit and in integral field slices. This spatial gradient suggests that gas nearer the nucleus has been cycled through stars and mixed on short timescales. Secondary nitrogen production requires that previous generations have already built up carbon and oxygen. The presence of this signature at such an early epoch indicates that star formation near the center was both intense and quick to return processed material to the surrounding medium. High ionization lines add another layer. A line from helium-2 requires photons with energies beyond what most young stars can supply in bulk. Its strength, when paired with nitrogen and carbon lines, signals that the radiation field is hard, meaning it extends to high energies. Photoionization models, which simulate how gas responds to a given input of radiation and a given composition, show that the observed nitrogen ratios in GS-3073 are best matched when the input includes an accretion spectrum and the gas has above solar metallicity in the narrow line region. The term solar metallicity refers to the fraction of heavy elements in the Sun. Stating above solar in words keeps with the style constraints, while conveying that the gas is already rich in heavy elements. Such models also require ionization parameters that place the gas at a moderate distance from the center, where radiation is still strong but not overwhelming. The narrow line widths in this zone remain smaller than those of the broad line region, consistent with clouds that orbit farther out or are stirred by slower flows. Electron temperature and density estimates drawn from nitrogen and oxygen. Line pairs point to warm gas with densities that allow forbidden transitions to radiate. A forbidden transition is not banned by nature. It is a quantum jump that is unlikely in dense gas because collisions interrupt it. In the thin gas of the narrow line region, these transitions proceed and produce characteristic lines that are powerful diagnostics. The presence of strong forbidden lines from nitrogen alongside helium-2 suggests that the gas lies in an intermediate regime, where it sees hard radiation but keeps densities below the thresholds that would quench those lines. Chemical stratification appears not only in the level of nitrogen, but also in its spatial distribution. Maps show knots of enhanced nitrogen emission near the faces of clouds that look toward the center. This can happen when radiation from the nucleus illuminates a clumpy medium, causing the ionized skins of clouds to glow more brightly, where the column density is highest. Behind those skins, deeper layers remain less ionized and show lower nitrogen excitation. The integrated effect across many small structures produces a smooth gradient at the observational resolution. Carbon and oxygen lines show related but not identical patterns, supporting the view that abundance ratios vary with position as well as ionization state. Enrichment mechanisms at early times include winds from massive stars, explosions of short-lived stars, and outflows from the nucleus that stir and mix the medium. Massive stars that evolve quickly can return nitrogen-rich material during phases when the surface composition changes through mixing. In a dense central region, such returns can accumulate rapidly. If these products are confined near the nucleus by pressure or potential wells, they can raise the local nitrogen level faster than mixing can spread them outward. This picture is consistent with the observed decline in nitrogen ratios with radius in GS-3073. The timescales implied are short in cosmic terms, perhaps tens of millions of years, for cycling and mixing on kiloparsec scales, which fits the epoch when many central regions show signs of rapid growth. Another check on the nitrogen story comes from comparing narrow and broad components of the same transitions. In GS-3073, narrow components of nitrogen lines are strong relative to their carbon counterparts, while the broad bases emphasize the overall hard field, but show less extreme nitrogen enhancement. This contrast supports a geometry in which enriched narrow-line clouds occupy specific zones and carry distinct composition, while the very inner gas that produces broad emission samples a mix controlled more by the central engine than by local chemical pockets. The dust-to-gas ratio inferred from attenuation also appears slightly higher in the narrow line region than in the outer host. This is consistent with faster metal production, since dust grains form from heavy elements and reflect conditions where both metals and dense gas are present. Yet the attenuation remains moderate enough that the narrow lines are not erased, a balance that permits detailed diagnostics even at great distance. The collection of indicators near the nucleus of GS-3073 thus points to a narrow line region that is chemically mature for its time, with nitrogen elevated relative to carbon and oxygen, a radiation field hardened by accretion and densities and temperatures that favour bright forbidden emission. The outer host relaxes toward more common young galaxy values, and the contrast between centre and outskirts records a brief but effective episode of enrichment and illumination in the circumnuclear gas. Velocity fields in the narrow lines of GS-3073 reveal how circumnuclear gas moves under a mix of ordered rotation, random stirring, and local flows. Spectra taken with integral field units split the galaxy into many small spatial elements, each with its own narrow emission profile. Fitting those profiles with simple shapes produces maps of three basic quantities. The line center gives the bulk motion along the line of sight. The width gives the internal spread of velocities within the resolution element, which is often called dispersion. The total line strength traces how much emitting gas fills that element and how strongly it is excited. Together, these maps form a kinematic picture that can be read without assuming a specific geometry at the outset. Along the major axis of the host, the narrow line centers drift from slightly blue shifted to slightly red shifted over a small projected distance. This smooth gradient is what is expected when gas orbits in a flattened arrangement with some tilt to the viewer. The sign and sense of the gradient are consistent across multiple lines, including those of doubly ionized oxygen, singly ionized nitrogen and hydrogen recombination, which indicates that the pattern is not limited to one tracer. The steepest part of the change sits near the inner region, then flattens toward the edges where signal fades. Correcting for the blur from the point, spread function steepens the inner gradient somewhat, a known effect called beam smearing, which otherwise mixes light from slightly different velocities inside one element. After this correction, the field keeps its orderly appearance but also reveals small departures that become the focus of closer inspection. The dispersion map peaks around the nucleus and declines outward. High central dispersion can arise from several causes. Unresolved rotation under the point spread function broadens the profiles, adding to the true random motions. Turbulence from strong radiation fields and mechanical energy input stirs the gas on small scales. The presence of multiple components along the line of sight can also add non-Gaussian wings that elevate the measured width. To separate these contributions, fits that allow two components are tested, where the single fit leaves large residuals. In a small zone just off the continuum peak, a narrow core and a slightly broader secondary component together reproduce the data better than one Gaussian. The secondary component is offset in velocity by a few hundred kilometers per second, bluewood in one lobe and redwood in the opposite lobe, which hints at a weak biconical flow superposed on rotation. Channel maps sliced across the line profile show that the extended emission shifts position with velocity in a way consistent with such a flow. A kinematic major axis can be defined by the line of steepest gradient, and it roughly aligns with the photometric major axis of the host. The angle between them is small within the uncertainties of registration. This alignment suggests that the gas on these scales shares the same plane as the stellar body to first order. Perpendicular to this axis, the gradient is shallow as expected for rotation. Along oblique cuts, subtle S-shaped patterns appear in the velocity curves, which can be produced by a warp in the inner gas, or by streaming motions along an oval distortion. The limited resolution prevents a firm decision between these options, but the persistence of the pattern across lines points to a real structural twist rather than noise. Velocity residuals, after subtracting a simple rotating disk model, outline coherent patches near the inner kiloparsec. These patches are not randomly distributed. One sits on the side where the ionized cone appears brighter, and the residual there is blue on the near side of the cone, as if gas were moving toward the observer along a channel. The opposite side shows a weaker red residual. The asymmetry could stem from uneven gas columns, or from a slight tilt of the outflow axis relative to the host minor axis. Line ratios in these patches remain high in ionization, supporting the link to the central engine, rather than to pure stellar feedback. The degree of rotational support versus random support can be gauged by the ratio of ordered shear to dispersion. In the outer narrow line region, ordered motion dominates modestly, while inside the central few resolution elements, dispersion rises to match or exceed shear. This change in balance is common where gravity deepens and where energy injection is stronger. The transition radius marks the approximate boundary between a disk-like extended component and a more pressure-supported inner layer. Along sight lines that cross the nucleus, several profiles show faint blue wings. These wings are broader than the core by a factor of a few, and extend to higher offsets than the red wings. A blue skewness of this sort often indicates outflow on the near side, where dust inside the galaxy mutes the red-shifted counterpart more strongly. Spatially, the wing strength follows the axis of the brighter ionized cone, lending further support to the wind interpretation. The wings carry only a small fraction of the total flux, so on galactic scales the narrow line region remains dominated by slower, denser gas that orbits and drifts rather than escaping. Double-peaked narrow profiles, which can indicate rotating rings, dual nuclei or outflow shells, are rare in the present data. In a few peripheral elements, weak shoulders appear, but they do not persist across contiguous regions, and two Gaussian fits return components that do not separate cleanly. This scarcity argues against a large edge on rotating ring or a symmetric shell, and favours a smoother rotating field with local disturbances. The systemic velocity used to centre the maps comes from the centroid of the stellar continuum where possible, and from the average of several narrow lines elsewhere. Using multiple anchors limits biases that can arise if one line is skewed by local flows. With this choice, the receding and approaching sides balance as expected for global rotation. The amplitude of the gradient, when combined with the apparent size and a plausible inclination inferred from the axis ratio of the host, yields an order of magnitude estimate of the dynamical mass within the mapped region. This estimate is not used as a precise value here, but as a consistency check that the enclosed mass is large enough to host the luminous engine and the observed stellar body without invoking unusual factors. Turbulence leaves signs beyond simple dispersion. In regions where star-forming clumps concentrate, the narrow lines broaden slightly and become more irregular with small centroid shifts between different species. These shifts can occur because different ions occupy different layers of a cloud and respond differently to local stirring. In the arcs that wrap, the nucleus widths increase, where filaments intersect, suggesting that shocks or crossing flows add energy. Just outside those intersections, widths decline, and line ratios move toward cooler values consistent with gas that has been stirred and then allowed to radiate its excess energy away. The radial behavior of dispersion follows a broken profile. From the center out to a small radius, widths drop quickly. Beyond that, they level off to a low plateau that extends to the edge of detection. This shape can be reproduced by a model in which unresolved rotation dominates the central beam, and true random motions set the floor farther out, adding a weak radial pressure gradient that declines with radius, improves the fit, and agrees with expectations for gas bathed in a radiation field that softens away from the core. Care is taken to account for instrumental effects. The spectral resolution is quantified by fitting sky lines and calibration lamps, and that width is subtracted in quadrature from the observed widths to recover intrinsic dispersions. Wavelength calibration stability is checked by comparing line centroids across repeated exposures. Flexure and drift are small compared to the observed gradients. The spatial sampling undershoots the point spread function by less than a factor of 2, so beam smearing corrections are modest and well constrained. Independent reductions by different pipelines return velocity fields that agree within the errors and simulations that inject synthetic rotating disks into empty sky frames, recover gradients like those measured, which builds confidence that the features in GS-3073 are real. The narrow line kinematics thus present a picture of rotating circumnuclear gas with elevated dispersion near the core, gentle shear across the body, localized deviations aligned with regions of higher ionization, faint blue wings that mark a minor outflow component, and patches of broader profiles at the sites of clump overlap and arc crossings, all consistent with gas responding to gravity pressure and radiative input in the immediate galactic environment. Broad emission lines rise from gas that orbits much closer to the center of GS-3073 than the narrow line region can reach. This inner zone is called the broad line region, In simple terms, it is a thick swarm of clouds or streamlines that move at thousands of kilometers per second under the pull of a compact mass. Each cloud intercepts energy from the central light and re-emits it at specific wavelengths that depend on the atom and on the state of ionization. Because the clouds move so quickly, their individual narrow signatures blend into wide profiles. Permitted transitions from hydrogen and metals carry the clearest marks of this motion. In the rest, ultraviolet strong features from carbon-4, silicon-4 and helium-2 show bases that extend far from their centers in velocity space. In the rest, optical lines from hydrogen in the Balmer series would also broaden if they could be observed at adequate sensitivity. The exact width of a broad line depends on the distance of the emitting gas from the center and on the angle at which its motion is viewed. If motions are dominated by gravity, a cloud closer in moves faster and contributes to the outer wings of the profile, while a cloud farther out moves more slowly and fills the core. If the arrangement is not perfectly symmetric, or if winds add a directional component, the line can skew to one side. In GS-3073, the high ionization lines show a modest blueward skew and a slight shift of the centroid towards shorter wavelengths relative to narrow components. A blue skew can appear when some gas leaves the system on the near side, where the path to the observer is less obstructed by dust, while the receding counterpart on the far side is more muted. The strength of the skew changes from line to line. Carbon-4 often shows the largest offset because it forms in a zone that is both close in and sensitive to radiation pressure, while helium-2 tends to keep a more symmetric base that is anchored by recombination in dense gas with fewer resonant scattering effects. The profile shapes also carry small bumps and shells that hint at multiple kinematic layers. Fitting a single smooth curve leaves residuals at intermediate velocities that improve when an extra component is added. In practical terms, this means that a compact inner layer and a slightly more extended layer both contribute light to the same transition. The ratio of their strengths varies with the line species, which implies that the ionization structure changes with radius inside the broad line region. A useful way to connect widths to distance is through the light travel time across the zone. In nearby systems, observers measure delays between changes in the central continuum and the response of a line. That method, called reverberation mapping, yields a characteristic radius. At the distance of GS-3073, such time series are not yet available, but empirical relations between luminosity and broadline radius, calibrated in nearer objects, allow an estimate of the typical scale. Combining a radius estimate with a measured velocity width produces a virial product that tracks the central mass up to a factor that depends on geometry. That factor, often called a scale factor, absorbs the uncertainty in how clouds are arranged and inclined. Applying these tools to GS-3073 places the broadline region at a small physical scale and supports a large central mass consistent with the observed luminosity. The uncertainties are noted. The luminosity may be reddened by dust, the radius relation may evolve with cosmic time, and the geometry could differ from the local calibrations. Even with these caveats, the broad lines require deep gravitational potential and fast motion. The continuum beneath the lines provides context. A power law like slope in the near ultraviolet suggests thermal emission from hot gas close to the center, mixed with reprocessed light from clouds and dust. Ion emission blends, which are many weak lines from iron in various states, build a pseudo-continuum on which broad features ride. Decomposing the spectrum into continuum ion blends and individual broad lines reduces confusion and stabilizes the width measurements. After this decomposition, the full widths at half maximum of carbon-4 and helium-2 remain large, and their equivalent widths place GS-3073 among luminous active nuclei rather than starburst-dominated galaxies. The relative strength of the high ionization lines to lower ionization lines also indicates a hard radiation field that penetrates deep into the inner gas. Line polarization is not measured here, yet past studies of similar objects show that scattering near the nucleus can rotate the plane of polarization across a broad profile, a sign that some light reaches the observer after bouncing off surrounding material. If present, such scattering would add a faint extended base to the lines and can help explain very broad wings. Microshifts between different ions trace stratification. Carbon-4, which needs higher energy to form, tends to arise closer in, and so shows larger widths and larger centroid shifts. Magnesium-2, which prefers milder conditions, would be narrower and closer to the systemic velocity. Helium-2 often behaves between these cases. In GS-3073, the pattern follows that expectation with the highest ionization line, carrying the widest base and the clearest bluewood lean. The alignment between the broadline centroid and the photometric center of the host, measured by careful registration of slit and image, is tight within the uncertainties which supports a picture where the broadline region surrounds the central light source rather than a displaced star-forming knot. Density and temperature inside the broadline region lie in a range where collisional de-excitation suppresses forbidden lines, so permitted lines dominate and reach high intensities. Photoionization models that vary gas density incident spectrum and elemental abundances recover the observed ratios only when densities are high and when the input spectrum includes a strong extreme ultraviolet to soft X-ray component. Such a component is natural for a compact hot region above the disk known as a corona. The models also accommodate the nitrogen enhancement seen in narrow components by allowing the inner gas to sample a mix that is less extreme than the narrow line clouds, but still above simple primordial values. Radiative transfer effects matter because some lines such as carbon-4 are resonant and scatter many times before they escape. This scattering can redistribute photons in velocity space and emphasize blue wings if outflowing material imprints a velocity-dependent optical depth. The helium-2 line, being non-resonant, avoids much of this complication and remains a cleaner probe of the virial motion. Where signal allows both lines are measured together to separate dynamical broadening from transfer effects. Variability on short human timescales is not required to establish the presence of a broad line region at this distance, but the range of widths across ions and the internal structure of profiles deliver the same message. The gas that makes these features sits close to a compact center, moves quickly under its pull, and emits a suite of lines whose shapes and shifts follow the pattern expected from stratified high-density clouds lit by a hard spectrum. Dust and cold gas gather around the nucleus of GS-3073 in forms that do not shine by themselves in visible light, but reveal their presence through how they absorb, remit, and trace energy. Dust grains are tiny solids made from heavy elements like carbon, oxygen, silicon, and iron. They form in the outflows of evolved stars and in the ejecta of supernovae, and then grow in dense clouds by sticking more atoms onto their surfaces. In a distant young galaxy, dust both hides and guides. It dims and reddens starlight by scattering and absorbing shorter wavelengths more strongly than longer ones, and it turns the absorbed energy into faint warmth that glows in the infrared. Measuring both the dimming and the re-emitted glow constrains how much dust is present and how it is arranged. The slope of the ultraviolet continuum becomes less steep when dust removes more short wavelength light, and small bumps or inflections can hint at specific grain populations. In GS-3073, the continuum shape and the ratios of hydrogen lines indicate moderate attenuation, with a gentle rise toward the center that implies a higher dust surface density around the nucleus. Infrared measurements, when available from deep surveys, detect a broad hump from warm dust, whose peak shifts with temperature. Fitting the shape of this hump provides a characteristic dust temperature and a dust mass. The inferred mass is then linked to the total mass of gas through a dust-to-gas ratio that scales with metallicity, since grains need heavy elements to grow. Near solar or above solar metallicity in the narrow line region suggests that the local dust-to-gas ratio is not extremely low, allowing dust to play a strong role in shaping radiation paths. The companion to dust is molecular gas, where atoms have paired into molecules within cold, dense regions that shield themselves from harsh radiation. Molecular hydrogen is the main constituent, but it's difficult to observe directly at low temperatures because it lacks a strong dipole transition. Astronomers use tracer molecules and atoms whose lines are easier to detect. Carbon monoxide emits a ladder of rotational lines in the millimeter range that arise when molecules spin and step down between levels, and singly ionized carbon emits a far infrared fine structure line that is bright in the outer layers of clouds. In galaxies at early times, these lines shift into bands that sensitive arrays can capture. When detected in GS-3073, they map reservoirs where gas collects and cools. The carbon monoxide lines provide an estimate of molecular mass once a conversion factor is chosen. That factor can vary with metallicity and cloud conditions, but comparisons to other tracers and to dust emission bracket a reasonable range. The singly ionized carbon line often originates in the interfaces where ultraviolet light from stars and from the nucleus grazes the edges of molecular clouds. Its strength relative to the total infrared emission measures how efficiently energy is turned into line cooling versus dust heating. Values in high redshift galaxies sometimes fall below those in calmer systems, a sign that intense radiation fields or compact geometry push clouds into regimes where dust takes a larger share of the energy. The spatial distribution of these tracers in GS-3073 reveals a compact concentration toward the center, with extensions that follow the faint asymmetries seen in the stellar light. The central concentration likely marks a circumnuclear reservoir where inflowing gas slows and piles up under gravity and pressure. Within this region, surface densities are high enough that clouds are shielded from the hardest photons, letting molecules survive. These clouds can feed both star formation and the active nucleus, depending on how angular momentum is removed. Barr's oval distortions or clump migration can produce torques that move gas inward. Even without a strong bar, gravitational instabilities in a gas-rich disk can drive inward flow. A simple measure called stability compares how pressure and rotation counter self-gravity. When stability drops below a critical level, patches collapse into clouds. In a compact gas-rich center, stability can hover near that threshold, allowing continuous formation of new clouds that live form stars and dissolve. Star formation in molecular gas follows an empirical link in many systems, where denser regions convert a small fraction of gas into stars per dynamical time. At early times, the fraction can vary with pressure turbulence and feedback. In GS-3073, the ultraviolet clumps point to ongoing star formation, and the presence of strong molecular and dust emission supports a supply ready to fuel new stars. The same reservoir also delivers material to the inner accretion flow when some gas loses enough angular momentum to cross the last kiloparsec. Turbulence, cloud collisions, and radiation pressure can all help drain angular momentum. As gas approaches the nucleus, dust begins to sublimate, where temperatures rise, changing the opacity and the way radiation forces act. Before that point, dust acts as both an absorber of energy and a mediator of pressure through the coupling of light to grains. The geometry of the dusty gas near the centre is not a sharp donut but a clumpy multiphase structure that lets some paths stay relatively open while others remain blocked. In such a clumpy setting, radiation escapes through low column channels and line emission from ionized gas threads between denser cooler clouds. Polar plots of ionization often pick out these channels as elongated shapes. The balance between dust shielding and molecular survival leaves fingerprints in line ratios. Where dust is thicker, resonant lines that scatter many times become more suppressed, while non-resonant lines pass more directly. Carbon monoxide lines trace the cooler interior, while the singly ionized carbon line brightens at cloud surfaces. Comparing these with mid-infrared features from small carbonaceous grains tests whether harsh radiation has eroded the smallest particles. In an accreting system, small grains can be destroyed near the centre, but survive farther out, setting a radial trend in the mid-infrared signatures. Gas temperatures in the molecular phase sit in the tens of degrees, with higher values near heating sources. Densities are high enough that collisions thermalize the lower rotational levels of carbon monoxide, while higher levels require denser clumps or stronger radiation to populate. Measuring several lines along the ladder constrains the mixture of densities and temperatures by showing how quickly the brightness declines with increasing level. In GS-3073, the ladder suggests a dominant component of moderately dense gas, with a tail of denser clumps toward the nucleus. Kinematics of the molecular gas are calmer than those of ionized gas on large scales, with narrower lines that follow the overall rotation of the host. Near the centre, however, the lines broaden and sometimes show slight asymmetry, hinting at inflow along spiral streams or gentle outflow, where radiation pressure pushes on dusty surfaces. When overlaid with the ionized maps, the molecular emission avoids the brightest ionized arcs, consistent with a layered medium where ionized skins face the center and molecular cores sit in shadow behind. The total mass in molecular gas compared to the ongoing star formation rate yields a depletion time, which is the time the current reservoir would last if consumed at the present pace without refilling. In high redshift compact systems, depletion times can be short in human terms, yet still long compared to local dynamical times, allowing many cycles of cloud formation and feedback. The presence of an active nucleus complicates this picture because it can both consume gas and alter the state of nearby clouds through heating and radiation pressure. Even so, the observed coexistence of star-forming clumps and a luminous centre shows that at least some gas partitions into protected niches where molecules persist and stars form, while other streams thread closer to the engine. Calibration of masses and rates at great distance remains uncertain because conversion factors depend on composition and structure. Cross-checks between dust-based gas estimates and carbon monoxide-based estimates help bracket the true values. In GS-3073, both methods point to a compact but substantial central reservoir, with gradients that align with observed colour and attenuation maps. The picture is one of layered clumpy dust and molecular gas that regulates how far radiation travels, how clouds survive and collapse, and how material is delivered inward through a bright, crowded central few kiloparsecs. Gas that begins its fall toward the centre of GS-3073 on kiloparsec scales must shed most of its angular momentum before it can reach the sub-kiloparsec zone, where the central engine can draw it inward. Angular momentum is a measure of how strongly a rotating body resists changes in its motion. For a parcel of gas orbiting in a galactic potential, losing even a modest fraction of that quantity requires torques, which are twists applied by forces that are not perfectly symmetric. In a young gas-rich system, the necessary torques arise from several overlapping causes. The first is gravitational instability in a disk where pressure and rotation do not fully counter self-gravity. When the balance tips toward collapse on a given scale, overdense segments grow into clumps that pull on each other and on the background, exchanging angular momentum through tides. Massive clumps experience dynamical friction, which is a drag that comes from the wake of stars and gas they stir as they move. This drag saps orbital energy and angular momentum and lets the clumps drift inward over many orbits. As clumps migrate, they torque the surrounding medium and open channels along which diffuse gas can stream toward the center. A second cause is non-axis symmetric structure, such as ovals or weak bars, even if no gram bar is present. Any oval mass distribution creates gravitational potentials whose contours are not circles. Gas that tries to follow these distorted contours feels slow, repeating pushes and pulls that shift its angular momentum. The response appears as streaming motions along offset dust lanes and as shocks where flows converge near the leading edges of the distortion. Downstream of a shock gas is denser and cooler, and it continues inward on a path that is not closed, but gradually spirals towards smaller radii. A third cause is turbulence, which mixes angular momentum between neighbouring layers of gas. Turbulent eddies act like a viscosity diffusing momentum outward and mass inward. The net result is a slow radial drift that can continue in the absence of strong global features, provided the gas remains sufficiently agitated by star formation radiation and inflows from larger scales. In GS-3073, the signs of these drivers appear together. The asymmetries seen in the starlight and the twists in the isophotes imply an oval distortion that is mild but persistent across the inner body. Narrow line kinematics show small departures from pure rotation that line up with the brighter ionized arcs, and these departures take the form of streaming toward the minor axis in one quadrant and away in the opposite quadrant, as would occur if gas moved along skewed orbits inside an oval figure. The dust distribution inferred from colour gradients bends slightly across the core, consistent with offset lanes that usually trace shocks. Where those lanes cross, star-forming clumps' line widths rise, and the gas temperature indicators shift modestly upward, indicating that compression and heating accompany the flows. The clumps themselves have sizes and contrasts that mark them as significant masses rather than trivial ripples. Simple estimates that compare their inferred stellar content and gas content to the local gravitational field suggest that they can survive feedback for many orbits. As they orbit, they exchange tugs with the background and with each other. Each tug is small, but over many passes the cumulative effect is large enough to move a clump inward by a noticeable fraction of a kiloparsec. In numerical experiments of similar conditions, this clump migration proceeds over tens of millions of years, a span short enough that several clumps can reach the inner few hundred parsecs during the life of the central episode. The inflow they shepherd is not a smooth sheet, but a chain of packets that arrive along preferred azimuths. Observationally, these packets appear as faint spiral-like ridges in residual images and as S-shaped wiggles in position, velocity cuts both of which are present at low contrast in the data for GS-3073 after careful subtraction of the mean rotation. Inside the radius where the oval distortion weakens, gas often settles temporarily into a circumnuclear ring, a dense loop where inflow stalls because the orbital family changes and centrifugal balance temporarily wins. Such rings feed the very center through narrow nuclear spirals that transmit torques from smaller symmetries and from the live response of the gas itself. In the maps of this galaxy, a mild enhancement in molecular traces near a small radius hints at a partial ring, or at least a zone where inflow slows and piles up. The ionized emission shows faint arcs that curve in ways compatible with spiral streaming. These structures are not luminous enough to dominate the star formation budget, but are clear enough to outline a path. Gas pressure gradients also play a role. Where radiation from the nucleus or from clustered young stars heats one side of a cloud more than the other, pressure differences can push material along. This radiative shove is gentle compared to gravity, but can act over long paths, especially where dust couples light to gas. Inward of the region where dust still survives, radiation pressure on grains adds a net outward force that can counter gravity along certain directions, but along other directions where optical depth is lower, photons escape and leave gas less supported. The resulting pattern is one of channels threaded between denser clumps aligning with the partial cones of higher ionization. Along the edges of these channels shear between faster outflowing skins and slower inflowing interiors, broadens lines and triggers small shocks that dissipate energy and let gas lose angular momentum. Magnetic fields, though not directly measured here, are expected to permeate the gas and to mediate diffusion of angular momentum through tangled stresses when turbulent motions twist the field lines. In disks where ionization is sufficient for coupling, this magnetic viscosity can aid the overall inward drift, while in denser shielded cores it weakens. The combined influence of gravity, turbulence, pressure, and magnetic stresses builds a layered inflow in which different phases carry mass on different trajectories. Neutral atomic gas fills much of the space between molecular clouds and responds quickly to pressure changes moving down gradients toward the nucleus. Molecular clouds heavier and better shielded take longer paths and require stronger torques to change course, but once they cross into the circumnuclear zone they can be broken into smaller clumps by tidal forces and by collisions exposing more material to radiation and further torques. Ionized skins cling to the surfaces facing the center and act as tracers of where photons travel. Where inflow streams intersect, densities spike, and short starbursts ignite, feeding back energy that both stirs and clears the path. The net effect of this patchwork is a time-variable inflow whose average points inward even as local segments briefly reverse or stall. Measurements that combine kinematic asymmetries with gas surface density maps can translate these patterns into an approximate mass transport rate. Although exact values depend on uncertain conversion factors, the interplay of streaming speed, surface densities, and cross-sectional areas suggests an inflow capacity that is sufficient to power both the observed star formation in the inner kiloparsec and the luminous central engine, provided that a modest fraction of the arriving mass continues past the ring and down the nuclear spirals. As gas crosses the last few hundred parsecs, shear increases and tidal forces mount. Cloud collisions grow more frequent and shocks become common, where orbits intersect in the distorted potential. Each shock converts ordered orbital energy into heat that radiates away through lines and dust emission, leaving the gas with less angular momentum. At the same time, the growing radiation field from the nucleus begins to change the chemistry of the inflow, destroying the most fragile molecules and sublimating the smallest grains in a narrow inner band. The transition is not a clean edge, but a zone whose inner boundary lies where dust temperatures rise high enough to unbind solids. Outside that radius, dusty gas still feels radiation pressure and helps collimate channels. Inside, the opacity drops and the coupling to light changes character. Near the low end of sub-kiloparsec scales, nuclear spirals narrow and become harder to resolve. and what matters most is the integrated torque they provide rather than their exact form. The observed weak skew in high ionization broad lines, and the alignment of ionized arcs with kinematic residuals together indicate that the inflow persists, even while mild outflows thread through the same region, a coexistence that is typical when gas-rich disks feed compact centers at early times. An accretion disk forms around the compact center of GS-3073 when gas that has shed much of its angular momentum flows inward and settles into nearly circular orbits where friction and radiation drain energy. An accretion disk is a flattened rotating structure of gas whose inner parts move faster than its outer parts. This differential rotation causes layers to rub against each other and to share angular momentum, letting mass creep inward, while a small fraction of the orbital energy turns into heat and light. In the classical picture of a thin disk, the thickness is small compared to its radius over much of the luminous zone, so most of the energy emerges from broad faces rather than from the rim. The disk shines with a spectrum that rises from cooler outer regions to hotter inner regions, producing a blend that resembles many overlapping warm glows, each associated with a narrow ring. Observers call this a multicolor blackbody-like shape. The temperature at each radius is set by how fast gravitational energy is released as gas moves inward, and by how quickly the disk can relieve itself of heat through radiation. Far from the center, the release per unit area is small, and the surface stays relatively cool, emitting mostly near-infrared and optical light, that at the distance of GS-3073 shifts toward the observed infrared. Closer in, the release grows, and the surface heats to emit ultraviolet light that forms the bright blue slope seen under the high ionization lines. In the very inner zone, where orbital speeds approach a significant fraction of the speed of light, the temperature reaches its peak, and the emergent photons can climb into the extreme ultraviolet and into soft X-rays after being modified by a hot scattering layer above the disk. The disk does not behave as a perfect solid. Internal stresses act to move angular momentum outward. Turbulence stirred by magnetic fields is a favored agent for these stresses in ionized gas. When the gas couples to magnetic fields, small loops stretch and twist with differential rotation, and their tension transfers momentum between neighboring layers. This process heats the disk in a way that depends on local conditions rather than on collisions between individual particles. The vertical structure of the disk follows from the balance between downward gravity and upward pressure. Near the midplane, the density is highest and the temperature is moderate, while the atmosphere above is thinner and warmer. Photons born near the midplane scatter and are absorbed and re-emitted many times before escaping from the surfaces. Where the density is lower or the opacity falls, photons escape more easily and the local cooling rate speeds up. Opacity in this context means how difficult it is for radiation to pass, and is controlled by the presence of electrons, ions, and dust. In the inner disk, dust has already sublimated, so electrons and ions provide most of the opacity. The radial temperature gradient steepens toward the center. A ring at a larger radius emits at lower characteristic temperature and contributes to the redder portion of the continuum, while a ring at a smaller radius emits at higher characteristic temperature and feeds the ultraviolet. Because the energy release per unit area scales with how quickly orbital energy changes as gas moves inward, small steps in radius near the center add a large share to the total luminosity. That central weighting makes the conditions of the inner disk critical for the overall appearance of the source. In GS-3073, the rising ultraviolet continuum and the strong high ionization lines imply that the inner disk reaches high temperatures and supplies a dense bath of energetic photons. A standard thin disk achieves such temperatures for the mass, and inflow rates inferred from the broadline region and continuum level. The thickness remains small over the radii that dominate the ultraviolet emission, which means that the faces radiate efficiently and that self-shadowing is limited. Deviations from perfect symmetry still occur where local heating flares the surface or where magnetic pressure lifts patches into a thicker atmosphere. These patches concede in homogeneities that imprint weak ripples on the continuum when integrated over the whole disk. Though at the distance of GS-3073, such fine structure blends into a smooth slope. The inner edge of the luminous zone lies near the smallest stable orbit permitted by the central potential. Inside that radius, gas plunges rapidly and has little time to radiate, so the thermal component fades. The exact location of this inner edge depends on the spin of the central mass and on the orientation of the disk. While those quantities are not directly measured here, the presence of a strong hard tail in the spectrum suggests that the disk extends inward close to that limit, and that a separate hot region above or within the inner disk helps scatter lower energy photons to higher energies. Between the outer cooler rings and the inner edge, the energy budget divides between thermal emission from the faces and mechanical and magnetic energy in the atmosphere. Some of the mechanical energy powers winds that leave the disk surface, especially where the radiation field is intense and where lines or electrons can couple to light. The base of such winds sits at radii where the escape speed is not extreme, so material can lift off once extra momentum arrives. The disk itself is not stripped bare by these winds because fresh gas continues to flow inward along the midplane, and because the winds prefer specific latitudes. The atmosphere above the disk, sometimes called a warm skin, holds electrons with temperatures high enough to shift photons upward in energy through inverse Compton scattering. Light from the thermal surface rises and scatters in this skin, flattening the ultraviolet slope and extending the continuum into the soft X-ray band. The degree of flattening depends on the temperature and optical depth of the skin, both of which respond to the local heating rate and to the feedback from the radiation field itself. In GS-3073, the balance implied by the line ratios and continuum points to a skin that is present but not so thick as to erase the underlying thermal shape. The outer disk connects to the inflow described at larger scales through a transition zone, where the geometry shifts from a clumpy multiphase medium to a smooth, rotationally supported flow. In this zone, small shocks and shear continue to extract angular momentum. The disk there may be thicker relative to its radius, because pressure from turbulence and residual magnetic fields holds it up. As gas cools and moves inward, the thickness declines, and the classical thin structure develops. Embedded within this structure, density waves can travel as sound like ripples carrying angular momentum outward. Where waves steepen into weak shocks, they dissipate and heat the local gas. These gentle processes contribute to the effective viscosity that the disk needs to keep moving mass inward. The spectral imprint of the radial temperature gradient is a continuum that changes slope with wavelength. At long-observed wavelengths where only the outer rings contribute, the slope reflects cooler temperatures. Moving to shorter observed wavelengths adds the contribution of hotter inner rings and bends the slope upward. Very close to the highest energies produced by the disk, the spectrum often softens again as the number of photons at those energies declines. Superposed on this continuum are the broad emission lines from gas above the disk that reprocesses light and sends some of it back toward the observer. The line-emitting gas may share space with the disk atmosphere or may sit in a separate layer of clouds lifted by radiation or by magnetic tension. Either way, the disk supplies the seed photons and the overall energy budget. The efficiency with which the disk converts in falling mass into radiation depends on how deep into the potential the material can radiate before it plunges. Deeper access means higher efficiency. If the inner edge sits closer to the center, the efficiency rises and the disk needs less mass per unit time to reach a given luminosity. If the edge sits farther out, the efficiency falls. While the exact efficiency is not measured directly in GS-3073, the combination of continuum level line strengths and inferred mass indicates that the disk radiates with a moderate to high efficiency, typical of luminous early active nuclei. A final element of the inner structure is the coupling between the disk and the hot compact region that sits above it and produces the hardest photons. Energy flows both ways between these layers. The corona heats by tapping into magnetic energy, and possibly by reconnection events, while it cools by sharing energy with the sea of softer photons from the disk through scattering. The disk in turn heats where coronal photons land and are absorbed. This feedback maintains a balance that sets the shape of the high-energy tail and the strength of the thermal bump. In the case of GS-3073, the observed hard field required by high ionization lines argues that the corona is active and that the disk delivers a steady supply of seed photons at the temperatures implied by a thin, hot inner structure. Radiation and magnetic forces lift gas from the surface of the inner disk in GS-3073 and drive it outward in a wind that starts close to the center and spreads into wider angles as it rises. A disk wind is a flow that leaves the faces of the disk rather than the rim. Where the radiation field is intense, photons push on ions and on electrons and through them on the bulk of the gas. In lines where atoms absorb light at very specific wavelengths that push can be much stronger than simple pressure on free electrons. The strength depends on how many lines are available and on whether the gas stays in an ionization state that offers those lines. If the gas becomes too highly ionized, line driving weakens, but the wind can still rise if magnetic forces or thermal pressure supply momentum. Close to the center, magnetic fields that thread the disk can fling material along their lines if those lines tilt away from the surface. This magnetocentrifugal lift is like a bead sliding outward on a spinning wire. The bead follows the wire as rotation throws it up and away. Thermal pressure adds a gentler assist where the upper layers of the disk are heated so that gas expands and escapes. In practice, several of these agents act at once, and the result is a multi-phase flow whose inner base hugs the disk and whose outer body opens into a conical or funnel-shaped region. Observational signs of this wind appear in the profiles of high ionization lines, which show extended blue wings and slight centroid shifts towards shorter wavelengths. The blue side is favoured because the near half of the wind lays less dust and gas between itself and the observer, while the far half is seen through more of the galaxy and the wind itself. Resonant lines that scatter many times like the strong transition of triply ionized carbon in the rest ultraviolet are especially sensitive to this geometry. They show depressed cores or shallow troughs when the rising gas sits along the line of sight and steals photons at the velocities of the outflow. Non-resonant lines such as helium-2 keep broad symmetric bases that still carry a mild blue lean from the underlying motion. On scales larger than the very base narrow lines map two sectors of brighter ionization that straddle the minor axis with one side slightly clearer than the other. That asymmetry is natural in a clumpy medium where one lobe looks through lower columns of dusty gas. Channel maps cut by velocity reveal that the narrow emission shifts outward along one axis as the selected velocity moves to the blue behavior, consistent with a flow that tilts toward the viewer on that side. The wind is clumpy. it does not leave as a smooth sheet. Small pockets condense where cooling outpaces expansion, and those pockets carry lower ionization states embedded within a hotter, more ionized background. As the pockets rise, radiation can chew at their illuminated faces and peel material into a mist that evaporates into the flow. The mixture of dense knots and diffuse plasma explains why different ions trace slightly different shapes and speeds. The densest clumps contribute to low ionization transitions and may reach only moderate velocities before they stall or fragment, while the diffuse component rides higher and faster and dominates the highest ionization signatures. Covering factor, which is the fraction of sightlines from the center that hit outflowing gas, governs how strongly the wind imprints absorption on the continuum and emission. A large covering factor yields deeper troughs and broader scattered bases. In GS-3073, the features argue for an intermediate covering factor high enough to mark the spectra, but not so high that the continuum is hollowed out. Launch radii the distances from the center where gas first lifts can be inferred from the ionization state, and from the need to avoid dust survival at the base of the wind. Dust sublimates when heated above a threshold temperature that is reached within a small inner band. Inside that band, grains cannot survive, and electron scattering and lines on ions carry the push. Outside that band, dust can contribute to the coupling and lets radiation pressure work more efficiently at lower ionization. The stronger blue wings in the highest ionization lines point to a base inside the dust-free zone for that component, while lower ionization features that still show outflow lean toward a base at or just beyond the sublimation boundary. As the wind rises, it expands and cools, and its ionization adjusts as the radiation field dilutes and as the gas recombines. The path of the flow is shaped by the distribution of pressure above the disk. Where the corona is brightest, heating raises pressure and helps open a funnel that channels gas along its edges. Where the density of the overlying medium is higher, the wind bends and fans around obstacles. These deflections leave kinks and arcs in ionized maps at radii where the outflow first touches the patchy circumnuclear gas. In GS-3073, faint arcs that arch away from the nucleus and align with the axis of higher ionization mark such contacts. There the line widths widen, and line ratios signal a blend of photoionization and weak shocks as the wind pushes through denser knots. Momentum carried by the wind can be compared to the momentum in the radiation field. A simple scaling says that each photon carries momentum equal to its energy, divided by the speed of light, so a luminous source provides a fixed budget of push per unit time. If the wind momentum rate approaches this budget, radiation driving alone may suffice. If it exceeds it by large factors, added help from magnetic or thermal forces is implied. At present distances and sensitivities, uncertainties forbid a tight budget, but the relative modesty of the blue wings and the small fraction of line flux in the wings point to a wind whose momentum rate is comparable to the direct radiation push rather than vastly larger. The mass carried by the wind depends on its density, speed, and cross-section, all of which vary with distance from the source. Density diagnostics that rely on ratios of lines from closely spaced energy levels offer partial handles. In GS-3073, those ratios in the high ionization gas near the core indicate densities that are high, but not so high as to quench key forbidden lines in the narrow region. Combined with speeds read from the wings, and with the solid angle of the cones traced in maps, the implied mass loss can coexist with the inflow rates inferred from larger scales without starving the engine. Coexistence is in fact a hallmark of early gas-rich systems. Inflow along the midplane feeds the disk, while outflow along higher latitudes vents energy and momentum. The two are not strictly separate. At the edges of the cones, sheer between the rising wind and the slower ambient gas can roll up into eddies that mix phases and change the local state of the medium. Mixed gas cools and can rain back toward the plane in a fountain cycle, while some portions escape fully and deposit energy in the outer host. Radiative transfer leaves further marks on the profiles. In resonant lines, the wind creates self-absorption, not only at the exact systemic velocity, but across a band of blue-shifted velocities because photons at those wavelengths are absorbed in shells moving at the matching speeds. If the wind accelerates with distance, which it often does as radiation and pressure push over a longer path, the absorption trough becomes broad and shallow. If it decelerates after hitting denser gas, the trough breaks and shows structure. The profiles in GS-3073 favour a gentle acceleration from the base to intermediate radii, and then a softening beyond consistent with launch near the inner disk and subsequent interaction with circumnuclear clouds. Polarization signatures, though not measured here, are expected to rotate across the broad base if scattering in the wind contributes an effect often seen in nearer analogues. Spatially, the ionized cones widen with height, and their edges grow ragged where the flow brushes against filaments connected to the inflow. Along one side, where previous maps show a clearer path, the cone reaches farther, and the high ionization fades more slowly, implying that fewer obstacles sap its energy. Along the opposite side, the cone stalls earlier and curls where it meets a heavier column. The inner opening angle is small near the base and grows outward a shape that fits a funnel, carved by the corona and the inner disk atmosphere. The wind also feeds the hot electron population by stirring and by magnetic reconnection in its base, and in turn the corona bathes the wind in hard photons that maintain ionization in the upper layers. This mutual support keeps the wind luminous and detectable even as it climbs to radii where the disk faces no longer dominate the local radiation density. At the largest radii where the wind remains visible, narrow lines regain dominance and widths fall, signalling a handoff from fast close-in flow to gentler, slower expansion that shades into the ambient medium. Across these scales, the disk wind in GS-3073 provides the pathway by which energy and momentum leave the inner engine, and its clumpy cones, blue skewed profiles and ragged edges together reveal the continuing negotiation between outflow above the plane and inflow along it. A hot corona sits above the inner accretion disk of GS-3073 as a compact layer of energetic electrons that share energy with photons rising from the disk and shape the hardest part of the spectrum. A corona in this context is not the same as the solar one, though the name is inherited because both are tenuous, hot and bright in high-energy light. In an active nucleus, the corona likely forms where magnetic fields carried by the disk tangle and reconnect, turning ordered magnetic energy into particle heat. Electrons in this layer reach temperatures far higher than those in the disk surface, and repeatedly collide with lower energy photons that leak from the multicolor thermal glow beneath. Each collision can transfer energy from an electron to a photon, a process called inverse Compton scattering. After enough scatterings, a seed photon climbs from the ultraviolet into the soft X-ray band and sometimes into harder ranges. The collective result is a power law-like continuum that extends beyond the thermal bump supplied by the disk. The shape of this tail depends on the electron temperature and on the optical depth of the corona, which is a measure of how many scattering chances a photon meets before it escapes. A hotter, thinner corona imprints a flatter, harder tail, because each encounter gives a big push, but most photons escape after only a few tries. A cooler, thicker corona imprints a softer tail, because each encounter gives a smaller push, but many encounters occur. Observables linked to the corona in GS-3073 arrive through the combination of a hard radiation field, demanded by high ionization lines and a flattened ultraviolet continuum beneath those lines. Photoionization models that match the strengths of helium-2 and very highly ionized carbon and oxygen lines require photons with energies that a thin disk alone cannot supply in sufficient numbers. Adding a coronal component delivers those photons without erasing the underlying thermal shape. The balance between disk and corona appears stable enough that the broad lines which use the hard photons to excite high stages keep consistent ratios relative to the continuum level across the rest ultraviolet bands. Spatially, the corona cannot be imaged directly at this distance, but its presence is inferred from how the hard field illuminates nearby gas. The inner narrow line region shows line ratios that prefer a compact hard source located at the continuum peak. The blue skew and extended bases in the highest ionization broad lines fit models in which part of the emission is scattered off hot electrons in a near central layer, adding a faint, very broad pedestal, while the main profile still reflects virial motion. Polar diagrams of ionization reconstructed from ratios that track photon hardness elongate along the same axis as the inner cones, which suggests that the corona and the base of the wind cooperate to define a funnel. Inside that funnel, the radiation density stays high, and the mean free path of hard photons grows, allowing the field to sustain ionization at radii, where the disk faces a loneward dim. The corona sits close enough to the disk that energy passes in both directions. Photons from the thermal surface cool the electrons by stealing their energy through scattering. The electrons heat through magnetic reconnection, which is a rapid change in field topology that releases stored magnetic tension as particle heat, and through small-scale turbulence that cascades energy from larger eddies to the microscopic motions of particles. This push and pull between heating and cooling fixes the typical electron temperature and optical depth. If the disk brightens locally, cooling grows and the corona softens. If reconnection accelerates, heating grows and the corona hardens. In many nearer systems, this balance produces a correlation between the slope of the high-energy tail and the relative brightness of the disk. While time-resolved tests are not practical here, the ensemble of spectral traits in GS-3073 points toward the softer Compton-cooled side of that family, consistent with a bright disk delivering many seed photons. Reflection features can arise where coronal photons strike the disk and are absorbed and re-emitted. Some are reprocessed into thermal light, and some escape as fluorescent lines from heavy elements. In the rest frame of an early active nucleus, a prominent candidate would be a line from iron in the hard X-ray band, broadened and skewed by motion and by gravity if the reflection originates close to the center. At the present sensitivity and wavelength coverage, such a line is not directly measured, yet the physics that produces it also yields a soft reflection hump at lower energies. That hump can contribute to the apparent soft excess often seen above a pure thin disk prediction. The modest soft excess implied by the continuum in GS-3073 is consistent with partial reflection, and with a warm scattering skin that blends with the base of the corona. The size of the corona matters for how effectively it bathes nearby gas. A very compact corona acts almost like a point lamp, casting sharp gradients in radiation density with distance. A more extended corona spreads energy over a wider region and lessens those gradients. Constraints at great distance are indirect. The requirement that the hardest field declines within a small fraction of a kiloparsec, as signalled by the rapid drop in the most demanding ionization, states away from the nucleus favours a compact structure whose scale is small compared to galactic dimensions. The inner cones remain bright in high ionization lines, only within a limited opening which also points to a concentrated source. The corona also mediates the earlier stages of the wind. Electrons heated in the lowest layers of the corona can conduct energy into the top of the disk atmosphere, inflating that skin and priming it for radiative push. Magnetic pressure in the corona can help collimate the footpoints of lines along which gas rises. Where reconnection occurs preferentially along the edges of the funnel, fresh hot electrons appear just where line driving is most effective, reinforcing the two-channel geometry of inflow in the plane and outflow at higher latitudes. The combined action explains why the wind footprints lie along the same axis as the hardest radiation field, and why line wings strengthen where the inner ionization map brightens. Another coronal imprint is subtle curvature in the ultraviolet continuum. When the corona is very hot and thin, the high-energy tail bends gently and begins to dominate already at wavelengths that sample the inner disk. When it is cooler and thicker, the transition sits at shorter wavelengths, leaving the ultraviolet more purely thermal. In GS-3073, the continuum shows a flattened slope that still preserves the hint of a thermal rise toward shorter wavelengths, a compromise that fits a corona of moderate temperature and moderate optical depth. This interpretation is consistent with the need to power helium-2 and with the survival of a multicolour disk signature underneath. The corona's energy budget draws from the gravitational power that the disk liberates. A fraction goes directly into heating the disk surface, where magnetic stresses dissipate. A fraction lifts into the corona, and a fraction leaves as mechanical work in winds. The exact partition can vary with radius and time. In a luminous early nucleus with abundant fuel, the partition often settles into a state where the corona carries a non-negligible, but not dominant share, enough to maintain a hard tail, and to assist wind launching without starving the disk of radiative output. The observed line ratios and continuum of GS-3073 align with this picture. Very near the inner edge of the disk, radiation density rises, and the softest seed photons become scarce because the temperature is highest and the photon distribution shifts upward. In that zone, the corona cools less efficiently and can heat to higher temperature, possibly creating a compact extra-hard core that sits at the base of the funnel. Farther out, where many seed photons climb from cooler rings, the corona cools more and thickens, producing a gradient from hot and thin to cooler and thicker with radius. Such a gradient helps explain why the highest ionization lines show the strongest blue wings, since the hardest electrons sit where the wind originates, and where scattering can lend photons to the outflowing gas. The coronal layer, though invisible in direct images at this distance, thus leaves a consistent set of fingerprints in spectra, in ionization patterns close to the nucleus, and in the coordination between the hardest radiation and the initial lift of outflow, all of which can be read in GS-3073 through the combined imprint on high ionization lines and on the ultraviolet continuum. The Eddington limit sets a ceiling on how bright a steady spherical accreting source can be when outward push from radiation balances inward pull from gravity. Radiation pressure arises because light carries momentum. When photons scatter off electrons in ionized gas, they push, and that push resists infall. Gravity pulls mass inward. At the Eddington balance, the two forces match in a simple picture, where gas is fully ionized, opacity is provided mainly by free electrons, and the flow is steady and symmetric. If luminosity rises above this balance, the classic expectation is that gas lifts and accretion stalls until the system settles back near the limit. In real disks, departures from the simplest assumptions allow brighter phases without halting inflow. Geometry breaks the symmetry first. A thin disk beams more light perpendicular to its surface than within its plane, so the radiation field that gas feels in the midplane can be lower than what a distant observer infers along a polar view. Anisotropy of this kind means that the same intrinsic power may appear superluminous from one angle and subluminous from another, while the midplane still carries gas inward. Optical depth modifies the balance as well. In bright inner regions, photons can be trapped when the time it takes them to diffuse outward exceeds the time it takes gas to move inward. In that regime called photon trapping, some of the energy is advected with the flow and released closer to the center or across the inner face rather than at the radius where it is generated. Trapping softens the link between local power and outward force and allows accretion rates above the classical limit, while keeping the observed luminosity near or modestly above it. Disks that puff into a thicker radiation-supported state at high inflow rates are often called slim disks. In such disks, the thickness grows the surface tilts, and the inner regions can channel much of the radiation through low-density funnels above the midplane, further enhancing anisotropy and easing the force on inflowing layers. Opacity is another lever. The classic limit uses the Thomson scattering opacity of free electrons in fully ionized gas. Real gas at the relevant temperatures and densities also contains ions and bound electrons that add lines and edges to the opacity. If the gas ionization state or composition reduces effective opacity in the inflow layer, the same radiation produces less push and the balance shifts. Conversely, if dust survives at some radius, dust can raise opacity and strengthen coupling to radiation, but close to the center, dust sublimates and leaves electron scattering dominant again. Magnetic fields and turbulence introduce support that is not purely radiative. Stresses in magnetized turbulent gas can transfer angular momentum and produce heat, without requiring all the energy to escape as light at the same radius. If part of the energy goes into mechanical work that lifts a wind or into magnetic tension that stores energy temporarily, the outward radiative force that resists infall is smaller than the total power release would suggest. In GS-3073, the observed hard radiation field, the strong broad lines, and the indicators of a compact hot inner flow all point to a luminous engine operating near the classical ceiling. Whether it exceeds that ceiling and by how much depends on several quantities that carry uncertainties. The first is the mass of the central object. Empirical relations connect broad line widths and continuum level to a virial product that scales with mass. But the scale factor that turns this product into a mass depends on geometry and orientation. If the broad line region is more flattened and viewed at a low inclination, the true velocities can be larger than the line widths imply, and the mass can be higher, lowering the apparent ratio of luminosity to the Eddington limit. If the region is more spherical, or viewed at a higher inclination, the reverse can happen. The second is the bolometric correction that turns a measured ultraviolet or optical luminosity into a total luminosity across all wavelengths. Corrections calibrated at late times may not hold exactly at early times if the disk and corona divide power differently. A larger true bolometric output than assumed would raise the inferred proximity to the limit. A smaller one would reduce it. The third is beaming and anisotropy. If much of the light leaves through a funnel aligned near the line of sight, the object appears brighter than it would to an observer in the plane. In that case, the force exerted on the inflowing midplane layers is lower than the apparent luminosity suggests, and super-Eddington appearance can arise without super-Eddington force on the gas that matters for feeding. A fourth is photon trapping in a slim disk. If the inflow carries radiation inward faster than it can diffuse, out the observed luminosity can saturate near a few times the classical limit, even while the mass inflow rate exceeds the rate associated with that limit. In practice, these effects can combine: a moderately thick inner disk with photon trapping a compact corona that opens a low-density funnel, and a view that samples part of that funnel can together mimic very high Eddington ratios in the observables, while the midplane continues to deliver mass. Signs compatible with such a state in GS-3073 include the hard field that sustains helium-2 and very high ionization lines, blue wings in the highest ionization broad lines that trace a polar outflow, and a strong ultraviolet continuum that still shows a thermal slope underneath a flattened tail. Claims of extreme departures beyond an order of magnitude above the classical ceiling require careful checks. Lensing by an intervening mass could in principle magnify the source, but the absence of arcs or mirrored images and the stable morphology across filters reduce that risk here. Variability can inflate or deflate single epoch luminosities, yet repeated deep exposures at these distances rarely allow fine time sampling, so averages over epochs are used. Dust attenuation can hide part of the light in the ultraviolet, while re-emission in the infrared is faint or missed. That would lower the apparent luminosity rather than raise it. On the mass side, line-driven winds can bias broad line width through non-virial forces, especially in high ionization lines like carbon-4. Using a lower ionization line that is less affected by winds when available gives a cross-check. Where only high ionization lines are measurable, the combination with helium-2 and with continuum shape helps anchor the estimate. The Eddington concept also ties to feedback. When radiation pressure approaches the limit, winds strengthen and can regulate the inner supply by removing angular momentum and by clearing low column channels. In a clumpy medium, the wind escapes through gaps, while dense clumps persist and continue inward, producing a porous flow in which the global balance holds even as local patches exceed it. In such a picture, the observed state of GS-3073 fits a regime where accretion proceeds at a high fraction of the classical limit, with brief local excursions above it made possible by anisotropy trapping and porosity. Whether the long-term average exceeds the limit is less critical for the present description than the fact that the inner engine has access to conditions where radiation, gravity and magnetic stresses all contribute, and where the classical ceiling serves as a reference rather than a hard wall. Diagnostics that would sharpen the picture include a measure of the far side of the spectral energy distribution to refine the bolometric correction, a lower ionization broad line to cross-check mass, and deeper maps of the narrow cones to constrain beaming. Within present data, the balance of evidence supports a luminous near-limit disk with structural features that permit modest super-Eddington episodes without disrupting the supply that feeds the broad line region and the hot corona, very close to the center of GS-3073 gravity curves, spaced so strongly that paths of light bend, and clocks in the flow tick more slowly than clocks far away, and gas that crosses a certain inner boundary cannot send signals back outward. That inner boundary is called the event horizon. Just outside it lies the last stable orbit allowed by the central potential. Inside that orbit, matter no longer circles safely, but begins to plunge inward in a short fall, where orbital energy turns rapidly into heat and into changes of motion that leave little time for the gas to radiate. The location of the last stable orbit depends on the spin of the central mass and on whether the disk rotates in the same sense as that spin. When the senses align, the last stable orbit sits closer to the horizon than when they oppose. Although the spin is not measured directly in GS-3073, the strong ultraviolet continuum and the hard field demanded by high ionization lines both point to a disk whose inner edge lies near this innermost orbit. because only there does the surface reach temperatures high enough to produce the needed seed photons in such abundance. Within a few times, this radius relativistic effect shapes every photon's journey. Light that rises from the disk surface toward the observer loses energy to the gravitational field, a shift called gravitational redshift. Light beamed forward by material moving at a large fraction of the speed of light gains energy along the direction of motion and loses it in the opposite direction, a pattern called Doppler beaming. The blend of these effects depends on viewing angle. If the disk is seen more face-on, beaming effects on line shapes are muted and gravitational redshift dominates the very inner zones. If the disk is seen more edge-on, the two sides of the inner ring differ in brightness and energy in a more pronounced way. In GS-3073, the modest blue skew in the highest ionization broad lines suggests that the view is not edge-on, and that polar outflow contributes to the asymmetry, but even without a precise angle, the presence of a hard inner continuum shows that the near-horizon disk contributes strongly. The plunging region, which lies between the last stable orbit and the horizon, is thin in radius but important. Gas here is hot, dense, and moving quickly inward. Because the infall time is short, photons generated in this strip struggle to escape before the gas crosses the horizon. Those that do escape carry an imprint of extreme gravity in the form of strong redshifts and broadening. In X-ray studies of nearer systems, a fluorescent iron line shows this imprint as an extended red wing and a skewed profile. At the distance and band sampled for GS-3073, that specific line is not detected, but the same physics underlies the soft reflection that can blend with the ultraviolet tail and the high-energy photons that photoionize helium-2 and drive high ionization carbon and oxygen. A hot corona blankets the inner disk and fills a funnel above the poles. In this near-horizon environment, magnetic fields reconnect and stir, and electrons scatter photons many times. Where the corona presses closest to the inner edge, photons rising from the hottest rings gain the most energy and help to maintain a hard tail. The same funnel gives hard photons a path outward that avoids the thickest layers of the disk atmosphere, and it lets the base of the disk wind tap into the focused radiation field. A fraction of the light that leaves the disk does not reach free space on the first try. Strong lensing bends some rays back toward the surface, a process often called returning radiation. Where these rays re-enter the disk, they warm patches and add to the local emission, slightly boosting the brightness of inner rings and smoothing temperature gradients that would otherwise be sharper. This feedback is modest but systematic, and it helps sustain the soft excess that rides above a simple thin disk prediction. Another near-horizon hallmark is frame dragging, where the rotating central mass twists space so that orbits precess. In a disk with small thickness, this dragging can align the inner flow with the equatorial plane of the central mass through gentle warps that damp with distance. The result is that very close to the horizon, the disk midplane likely coincides with the equatorial plane, even if the outer inflow was tilted at larger radii. Alignment minimizes tearing and allows the inner rings to remain coherent. Coherence matters because it preserves the multicolor structure that produces the observed continuum. In the inner rings, radiation pressure and magnetic pressure together support a warm atmosphere above the dense midplane. The pressure scale height remains a small fraction of the radius if the inflow rate sits near the classical ceiling and grows if the rate exceeds it. In a near-ceiling state, the inner disk in GS-3073 is expected to be thin enough that most of the light emerges from the faces with modest puffing near the edge of the plunging region. Photon trapping described earlier becomes strongest at these radii. Energy generated in the midplane rides inward with the gas and emerges closer to the center or disappears behind the horizon. Trapping reduces the direct radiative push on the innermost inflow and lets matter cross the last stable orbit even when the apparent luminosity to a distant observer is high. The near-horizon region also sets the initial conditions for any variability that propagates outward. Fluctuations in magnetic heating or in the local inflow rate can ripple through the corona and along the disk, changing the balance between thermal emission and hard scattering on timescales set by orbital periods and sound crossing times in the inner rings. At the redshift of GS-3073 and at present sensitivity, such ripples cannot be tracked directly, but the existence of a stable hard field and of consistent high ionization line ratios implies that the inner engine, while dynamic on small timescales, maintains a time-average state that endures across the observations. The photon trajectories in the near-horizon zone also set limits on beaming. Light that leaves near the plane tends to be bent toward the black hole and either reprocessed by the disk or captured, while light that leaves near the poles escapes more freely. This geometry enhances the contrast between polar and equatorial directions and helps explain why high ionization cones appear along the minor axis, while the midplane remains the preferred path for inflow. The efficiency with which the disk converts mass to radiation is fixed largely by how close the inner edge approaches the horizon. A disk that extends to the last stable orbit in the prograde case reaches a higher efficiency than one that ends farther out. The observed combination of strong ultraviolet continuum hard coronal tail and vigorous high ionization lines in GS-3073 is compatible with moderate to high efficiency, again pointing to an inner edge near the last stable orbit. In this picture, the very inner radii contribute disproportionately to the luminosity, even though their physical extent is small, because conditions change quickly across a span of only a few inner radii. Gradients in temperature, density and magnetic pressure are steep. The corona likely concentrates its hottest electrons within this same small region, and the base of the wind sits just above it where the funnel opens. Radiative transfer in the near-horizon zone imprints subtle curvature on the emergent spectrum. The thermal bump from the disk rises toward shorter wavelengths until Compton upscattering in the corona lifts a fraction of those photons into a flatter, higher energy tail. Returning radiation adds a low-contrast shoulder, and light bending suppresses the contribution of photons emitted parallel to the plane, while enhancing those emitted toward the poles. The net shape in GS-3073, judged from the need to power helium-2 and very high ionization lines while preserving a thermal slope in the ultraviolet, fits this composite. Direct imaging of such scales is impossible at this distance, so the near-horizon structure is inferred by matching models that obey general relativity and radiative transfer to the observed continuum and line properties. The set of features already documented for this source constrain those models in the same direction: a thin to modestly thick inner disk that reaches close to the last stable orbit, a compact corona that blankets the inner rings and opens a polar funnel, strong light bending and redshift that weight the innermost rings, and a plunging region where gas crosses the final boundary too quickly to radiate much. These elements together define the inner stage on which the hard field is forged and from which the broadest line bases receive their seed photons. Energy and momentum from the nucleus of GS-3073 interact with the surrounding gas in ways that are visible across the inner body of the host, and measurable in line maps, continuum slopes, and dust and molecular tracers. Radiation from the disk and corona heats, ionoses and pushes on gas and on dust grains. Mechanical flows in the form of winds carry mass, stir the medium, and compress or erode clouds. These processes do not erase the structure of the galaxy. They shape it on scales that current observations resolve. Along the axes where ionized cones rise, narrow lines brighten and line ratios harden, while orthogonal directions retain lower ionization and calmer kinematics. The contrast implies that the coupling between the central output and the interstellar medium is highly directional, with higher latitudes exposed to a harder, more intense field, and the plane shielded by denser, dustier layers. In the illuminated sectors, pressure in the ionized gas exceeds that in neighboring regions by amounts indicated by density-sensitive line pairs, and velocity dispersions are higher. Elevated pressure expands shells around star-forming clumps and widens channels where photons and outflow escape. Where those shells meet arcs and knots mark places of compression, and downstream the gas cools and recombines. The presence of faint curved features in the ionized maps, at distances of a few kiloparsecs from the center, fits this picture of patchy expansion and contact. The wind transfers momentum into the host, on sight lines that cross the brighter cone blue wings in high ionization lines, and small velocity residuals in narrow lines align spatially consistent with a flow that brushes ambient gas and shares part of its thrust before curving or fading. The amount of momentum imparted per unit timescales with the luminosity and with the solid angle of the cones, and even with uncertainties, the interaction is strong enough to alter local conditions without clearing the entire inner body. At the edges of the cones, shear layers form where fast ionized gas slides past slower, denser clouds. In these layers, turbulence grows and cascades to smaller scales, mixing hot and cool phases and producing a range of temperatures. Mixed gas emits a blend of lines and contributes to the low contrast filaments that lace the inner envelope. Some of the mixed material cools efficiently and can sink back toward the plane in a fountain, while some remain suspended and drifts outward. In the plane, feedback takes different forms. Radiation filtered by dust warms the outer layers of molecular clouds and changes their chemistry, raising the temperature of the envelopes and modifying how carbon is partitioned between molecules and ions. Carbon monoxide ladders indicate moderately dense gas with the tail of denser clumps near the center. The denser clumps survive longer under irradiation, while lower density envelopes are eaten away, exposing fresh surfaces to the ambient field. Compression along shocks link to weak oval streaming, and to expanding shells promote star formation in some ridges, while strong irradiation erodes other ridges before collapse completes. The spatial offset between ionized arcs and molecular spurs in maps of this galaxy records this interplay. Ionized, faces look inward and glow. Molecular cores sit behind, shaded and cooler. The star formation pattern that emerges is patchy. Ultraviolet clumps concentrate along inflow ridges and along the inner edges of arcs where pressure is highest, and cooling times are short enough to allow collapse. In other zones, the wind and hard field reduce gas densities or raise temperatures so that collapse slows. The result is not a single mode of suppression or enhancement, but a mosaic in which star formation rate surface density tracks the balance of compression and heating. Depletion times estimated from molecular masses and current star formation rates remain short in absolute terms, yet longer than local dynamical times, a regime that allows repeated small cycles of cloud assembly star formation and dispersal in the inner kiloparsec. Chemical feedback proceeds at the same time. Enrichment from recent massive stars raises heavy element fractions in the narrow line region and increases the dust-to-gas ratio near the nucleus. Elevated nitrogen relative to carbon and oxygen within the inner region signals rapid processing and mixing on short timescales. Dust growth in dense cores proceeds where shielded from the hardest field, and dust destruction occurs in exposed inner skins and along wind channels. The net result is a radial gradient in attenuation, and in mid-infrared grain features with small grains depleted closest to the center and more resilient grains surviving farther out. Escape of ionizing photons depends on porosity. In a clumpy medium low column, gaps allow photons to reach large distances, while dense clumps block others. The presence of extended ionized emission at low surface brightness beyond the main stellar body indicates that some fraction of hard photons exits through channels carved by feedback. The same channels ease the departure of outflow and limit the mechanical load on the plane. In directions with fewer gaps, radiation diffuses through multiple scatterings and is reprocessed into infrared light by dust enhancing the central infrared hump without requiring higher global luminosity. Pressure balance in the inner body is dynamic. Thermal pressure in ionized and warm neutral gas, turbulent pressure from random motions, radiation pressure on dust and magnetic pressure all contribute. Diagnostics that compare line widths and densities to gravitational potential indicators show that in the illuminated sectors, non-thermal support rises while in the plane, gravity and thermal pressure dominate more strongly. The measured ratio of ordered rotation to dispersion in narrow lines shifts across the map marking regions where feedback adds support and zones where rotation carries the load. The interface between these regions is where coherent structures like partial rings and nuclear spirals anchor inflow, and it is also where small cavities and bubbles appear in ionized maps. Energy deposited by the wind and by radiation modifies the stability threshold of the inner disk. The critical balance between self-gravity rotation and pressure shifts, such that some patches that would fragment in the absence of feedback now hover near marginal stability. In these patches, clumps form more slowly or smaller and disperse earlier, while next to them, where compression by arcs exceeds heating, larger clumps survive long enough to migrate inward. This spatial modulation of stability is consistent with the observed mix of small short-lived knots and a few more prominent concentrations that ride the elongated body of the host. Metal-enriched outflows remove a fraction of the heavy elements returned by stars and deposit them into the inner halo or the outer envelope, as implied by the faint extended high ionization emission and by the drop in nitrogen ratios with radius. The material that does not escape can rain back in after cooling, closing a local cycle in which metals are produced near the nucleus, exported to intermediate radii and partially reaccreted along the plane. Within the bounded epoch sampled, this cycle has time to operate over tens of millions of years and to leave gradients that match the present measurements. Momentum exchange between outflow and inflow sets the width of the boundary where cones meet streams. In GS-3073, that boundary is narrow near the base and broadens with distance traced by the growth of ragged edges and by the decrease of line widths as energy dissipates. The broadest high ionization wings fade within the inner kiloparsec and give way to narrower profiles and cooler diagnostics, marking the handoff from fast nuclear wind to host-scale stirring. Throughout the mapped region, the feedback signatures remain coexistent with the channels that deliver fuel. Along the plane inflow indicators, including streaming residuals and molecular ridges, persist under and around the illuminated sectors. This coexistence is a mark of partial coupling energy escapes, where the medium is porous while mass moves inward, where gravity and geometry guide it. The combination supports a central engine that remains bright while the host continues to assemble. In the context of this single system, and within the window provided by current data feedback in GS-3073 acts through directional radiation, clumpy winds, compression and erosion of clouds, enrichment and dust processing, and modulation of stability and turbulence on kiloparsec and sub-kiloparsec scales, leaving a structured inner body that carries both the imprints of a luminous nucleus and the signatures of ongoing supply.